Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're very happy to have Sergio Hart of the Hebrew University and the Center of Rationality to tell us about uncoupled dynamics and Nash Equilibrium.
Okay. So first thing I'm going to do is the following. That's not what I'm going to talk about. Okay. No. Eventually I'll talk about that. Now let's see. Light, whiteboard. Let's see. Does this make light on the...
If you say it loud enough, somebody will come in.
No. Okay. So I mean, as I told you, Val, I have lots of things that I can talk about, and so let me start with something. Weather forecasting. Okay, weather forecasting. Now let's assume that we have a forecaster that wants to forecast just rain, no rain. Let's assume that this is the 0-1 event, and there is a clear rule that decides whether a certain day there was rain or no rain. You know, above 1 millimeter is rain, below is no rain or something. So it's a 0-1 event. Now, here in the US, in Israel, forecast is tomorrow it's going to rain, or tomorrow it's not going to rain. Okay? Whatever. Depends on the season, yes? Now, those are serious forecasters. I'll tell you in a moment why. In the US, the forecast is 70% rain. Next day, it doesn't rain. You say, well, I only said 70%. What do you want? Okay? Or it did rain, you know? So it's very safe, you know, when you start saying percentage. If you say tomorrow it's going to rain and it doesn't rain, you are in trouble. So you see, forecasters in Israel have a harder job. In fact, in most of the world, I think that, I don't know in Europe what happens. Anybody has data on forecasting?
No percentages. I haven't seen percentages.
You haven't seen percentages, no. Or you go, you know, on Yahoo Weather or something, you get percentages, okay? Now, okay, so somebody gives percentages. How do we check if he's a good forecaster? Okay? So as I said, you know, he said 70%, it rains or doesn't rain, it's okay, yes?
So after the fact, you check them, right? Whether it rained on 70% of the days.
Okay, very good. So what we should do is the following. Let's look at all the days where the forecaster said 70%, okay? And let's see how many of those days were rainy days. If he's a good forecaster, should be close to 70%, right?
That's what they would claim, right?
That's what they would claim, okay? And we do the same with the days he said 50% and the days said 0% and so on. And that's how you can check if he's a good forecaster or not, okay?
Well, you just give the global average.
Okay, now I'm assuming, okay, so now here is one more data point. I know nothing about weather, neither statistically nor, you know, you can pick a spot on the globe that you want that you know nothing about, you can say, you know, and I can guarantee to you that I can be a very good forecaster for that spot. If you give me enough time, you'll see that I'm excellent.
Predict the weather from yesterday.
No. Against, not only against the actual weather that is there, even if I let Yuval decide whether there's going to be rain or not, and Yuval's aim, his real aim is to make me look bad. I mean, after he invited me here and so on, then, you know. So even against an adversary, I can be a very good forecaster, okay? So let's make this a little more precise, and I want to show you how game theory tells us something interesting here. So essentially what we have, think of it this way. We have a game, we have two participants. Let's call one the rainmaker, and the other is the forecaster, okay? And we have time that, let's say, those are the days, 1, 2, 3, and so on, that goes discretely. And the rainmaker at time t makes a decision. Let's call it rho t, which is 0 or 1, either rain or no rain, okay? The forecaster at time t makes a forecast, let's call it phi of t, okay, which is a number between 0 and 1. So 70% is 0.7 or something like this, okay? And Now I want to measure. I want to have a score to measure exactly what you talk about, how good the forecast is. And this measure is called the calibration measure. So calibration. So let me define the calibration measure. Okay? So suppose I am at time capital T. After 1,000 days, 3 years time or something, I'm looking at what this forecaster did. So what I'm doing is the following. I'm going to look at each one of the possible forecasts. So there's going to be here a sum over all alpha in 0, 1, which are all the forecasts that essentially appear. And for each forecast alpha, I'm going to look at the distance between alpha and the actual proportion of rainy days. Okay? So here I'm going to have, okay, so this is, let's call this NT of alpha. Let's call this RT of alpha. So this is going to be number of t less or equal t such that phi of t was alpha. So those are how many days in those 3 years the forecast was alpha. And this is going to be the number of t less or equal t such that phi of t was alpha and rho of t was 1. How many rainy days were among those days in which the forecast was alpha? And this ratio, for a good forecaster, should be exactly alpha. Or as close to alpha as possible. It's sometimes hard, especially if alpha is a non-rational forecast. Which, yeah, okay. And, sorry?
I just backcast.
One moment, we'll get to that. Now, I just want to weight this. Of course, we take, so this is the distance. How far 70% forecast is from the actual proportion of rainy days during those. And I'm averaging this, so I'm multiplying this, say, by NT of alpha divided by T. So if there is a forecast that was given with very low frequency, then clearly the distance there will get a low proportion. So that's an average distance. Okay? If you don't like the L1 measure, you want to put here an L2 measure, that's fine, or 17, it's the same. Okay, so I'm coming to the rules of the game. Okay? So the purpose of the forecaster is to make this as small as possible. Okay? And I'm going to show you that he can do it even against a very tough adversary. So I'm going to assume that the rainmaker is as adversary as possible, which means at every date, so let's now see exactly what the rules of the game are. Every date T, independently, the rainmaker decides rain or no rain, and the forecaster on forecast. After that, they both observe the forecast and the rain, no rain. And they have good memory, so they remember all this. So the rainmaker and the forecaster can condition what they do tomorrow on everything that has happened in the past. Okay? And I'm assuming that the rainmaker, so the rainmaker is not an oblivious rainmaker, but is one that may even want to make the forecaster look bad. Yuval. Yes? I mean, that was Yuval in my story, I meant. Yeah. Okay. So, okay. So the rules of the game, I hope, are clear. Okay. So theorem. Okay. F can guarantee. Let's call this thing okay. So let's say this is CT. That's a calibration measure at time t. Can guarantee CT goes to 0 as t goes to infinity with probability 1. And by guarantee, I mean no matter what the rainmaker does.
What does probability mean?
Okay, the probability will come from the fact that the rainmaker can make a probabilistic decision. And I can make a probabilistic forecast. Now, careful, probabilistic forecast doesn't mean I'm saying for sure 70%. It means with probability half, I'm going to say 70%. With probability half, I'm going to say 50%. That's a probabilistic, I can use a mixed strategy, okay? And that introduces a probability space, so that's where this almost surely happens, so with probability 1, okay?
So do you assume anything on that? Can my probability today depend on your probability?
Nothing. That's what guarantee means. No matter what.
Everything can only depend on the past, not the future.
Sure, of course, sorry. There are no prophets here, yes? Okay, so there nobody. So at date t,
Depend on your probability distribution or just on your outputs?
no, at date t, what we both know are the realizations of what has happened until that point in time. Okay? So if your question is, do I know with what probabilities you chose whatever you chose, or do I only know what actually has happened? The answer is I only know what actually has happened, even though that will not make much difference. Okay? But that doesn't make much sense. How do I know what probability you are using? I can only see what happens. Or how do I know what, okay? Question?
So what happens if I say a distinct alpha for every day?
If you say distinct alpha every day, that's fine. What's going to happen is that this is going to be 1. Okay? Only one once. This is going to be either 0 or 1. So you're going to look at the distance between whatever alpha and either 0 or 1, which is going to be usually quite large. Remember, all these numbers are between 0 and 1. So large, 0.1 is large. Okay? Okay. So let me give you one proof. Okay? So let me remind you first about the minimax theorem.
Let me ask you a question.
Yes.
So I obviously don't like that.
Oh, very good, very good. No, no.
Your purpose.
That's my purpose, of course. No, sorry. My purpose is not that you don't like it, but to convince you that not only you, but nobody should like this. Okay? So it's fine. So
Is that, so my first intuition would here, I mean, already when I saw this definition, I started to suspect that sort of the forecaster can just predict the past and then he's very well off. So I don't
no, but you cannot. I mean, if you are facing a stationary, if you are facing a stationary environment, then yes. But you are not facing a stationary environment. You are facing Yuval, who remember, he is going to try to mislead you.
But I think your measure does not really measure how good I predict tomorrow.
Okay.
That's exactly what he said.
That's what, very good. So can you keep this point in mind and let's come back to it. But first let's show that indeed I can do what I claim. And then let's see whether this is worth anything or not.
So do you have an error theorem that you say no matter what measure you put there?
No. I mean, no. The answer is no. There is a way to do it, but it's tough. Okay? Okay, so now let me go back. Yes, I started saying the minimax theorem. What does the minimax theorem say? If you have a two-person game, where what's called the zero-sum game, which means that one player pays to the other. Okay, so there are only transfers between the two players. Okay, and I'm looking at what then here is a way to state the minimax theorem, which says the following. Assume that for every strategy of the second player, I have a strategy that will give me a payoff of at least 7. So for every strategy of player 2, I have a reply that may depend on his strategy, of course, that will give me a payoff of 7. Then I have a strategy guaranteeing me a payoff of 7 without knowing anything about what he does. That sounds almost impossible, yes? Right? You are okay. That's a minimax theorem, yes? That's a minimax. I mean, you write the theorem as min max equals max min, everybody does. Oh, okay, yeah. What does it mean, okay? But I think phrasing it this way, it's surprising, and then you understand that there is something to it, okay? But of course, there are conditions, yes? That's not true for any game. Yes, if we take a game, whoever is going to say the highest integer wins, then clearly this theorem does not apply. That's a nice exercise for you to try at home. and you can, it's safe, believe me. Okay, so in a finite game, where when I say strategy, I mean a strategy including mixed strategies, so I can use probabilistic mixtures. So if for every mixed strategy of the second player, I have a strategy of mine that gives me a payoff of at least 7, then I have a mixed strategy of mine that guarantees at least 7 no matter what the other does. That's a minimax theorem, okay? Which, mathematically it's a separation theorem, but it has a nice thing. Of course, this is true also with 8 and 9 and 2 and 2 and 9. Yeah? Okay, so now let me show you how I can use the minimax theorem to prove this. So let's assume I take t large enough, and we'll see later how big t should be, okay? 1,000, okay? And let's assume I want to get this to be within, let's say, 6%. I'll tell you why in a moment why 6%. In fact, 5%. So I'm only going to use forecasts that are multiple of 10%. I think that's what they use here, right? So with forecasts, so I'll tie my hand. So with forecasts that are multiples of 10%, of course, I can never get closer than 5%. Because maybe the true probability is 25%. I can only say 20 or 30. So 5% error is always there. There is no way to rid of it. I can get it 6%, or in fact 5% plus epsilon for any epsilon. Okay? So let me show you how I get 6% error. So how do I get this measure to be something of the order of 6%? Okay? So what I'm doing is this. I'm looking at this game. At every period, it's a finite game. Because at every period, this guy has 2 actions. This guy, if I take multiples of 10, has 11 actions, 0%, 10%, up to 100%. And of course, they can condition the actions of what happened in the past. Still, the number of strategies is finite. It's a big number, but I don't care. It's a finite game. If it's a finite game, then let's assume that I know what the strategy of the rainmaker is, and let's see if the forecaster can guarantee 6% calibration measure. Well, if the forecaster knows the strategy of the rainmaker, what does it mean? At every point in time, given what has happened until that point, the strategy of the rainmaker tells him rain or no rain or some probability of doing that. So he knows exactly what is the probability of rain tomorrow. What's going to be the forecast? Rounded up to 10%. Okay? That's it. If he does that, what's going to happen? Let's look at all the periods when the forecast was 70%. Those are exactly the periods where the conditional probability of rain given the past was between 65% and 75%. If the number of such periods is large enough, law of large numbers says it's going to be between 65% and 75%, and I took another 1% for the error of the law of large numbers. Okay? Now that's true for 70% and 60% and so on. So,
wait, I have a problem with it, which is that you said
but I haven't finished. Wait, no. Let me finish. With the application of the law of large numbers?
yes.
No, you put the errors. What happens is you weight it since those things that appear that appear very few times, their weight is small. So that's automatically taken care of. It's only the things that appear with big weight. Those forecasts that have been used with big frequency, with large frequency that matter. So this takes care of itself neatly. Okay, don't worry. Let's go. That's no. I mean, it's a computation, but it's simple. Okay, so I've showed you that if we take a given strategy of the rainmaker, the forecaster can guarantee that C is going to be less than 6%. For T large enough, how large should be T? Well, from the law of large numbers, we know how large T should be. So if for every strategy of the...
T now is larger than your
No,
state.
T should be like 1%, 1 over 1% squared, okay? That's what, 1 over epsilon squared. That's the order of magnitude. So I know exactly what it should be. We have good estimates for the law of large numbers, okay?
If T gets larger,
No, I'm talking about fixed. No. I said fixed T. I'm going to take T large enough, and I know how large it should be as a function of that epsilon, that 1% error that I allowed myself. That tells me what T, and I'm working with a fixed T. So I'm showing you that for...
exponential in the fixed T. So therefore
No.
determines the law of large
No. It's not. But let's not get into that. It's not. It's a detail. We can sort it out later. Okay. So the point is this: if for every strategy of the rainmaker, I showed you that there is a way for the forecaster to get 6% calibration error. Well, that means he can guarantee 6% calibration error without knowing anything about what the rainmaker does. That's a minimax theorem. That's it. End of proof. Now, how do you do it? The minimax theorem doesn't tell us. Yes. Okay, but I'll tell you. Okay, I'll tell you. There is in fact an easy way to do it. Okay, and so this is an existence. So this was an existence proof that doesn't tell us anything, but there is a nice constructive way to do it, and that's based on something else coming from game theory, which is, in fact, this I have already. You know what? Now I can switch. But now this screen is off. That's very nice. Okay. So light control. I even pressed the wrong button by mistake.
The right button.
Yeah, good. That's really surprising. So no, because also 3 separate buttons, and for miraculously they all. Yeah. Okay. Okay. So now. Sorry, wrong. I'm now going to juggle between presentations and keep taking something from, okay, and keep taking from each one something. And if you want more details, I'm going to be here another week, so I'll gladly tell you more about things that may interest you, or I'll gladly not tell you anything more. So your decision. Okay, so approachability. So assume now that we have a two-person game, or we have a game where payoffs, rather than being numbers, are vectors, n-dimensional vectors. First coordinate is apples, second is bananas, third whatever, so those could be different commodities. Those could be, for example, what's called contingent commodity. That's money if it rains. That's money if it doesn't rain. Or if I'm sick or not sick. Or those could be other things. So there are various models where one, in fact, wants to talk not about one payoff, but about more than one payoff, which there is no natural way to make out of them one number. Okay? So that's approachability setup. So what we have is, so what we have here, we have player I, me if you want, well, one player, and all the rest of the players, let's say second player. And in each box now we have, let's say here m equals 2, so we have two numbers, apples and bananas, let's say. Okay, so those are, first coordinate is apples, second coordinate is bananas. So if player 1 chose the top, if player 1 chose top and player 2 chose left, this is how many apples player 1 gets, this is how many bananas player 1 gets. Okay? Now, so that's a setup. That's David Blackwell, 1956. Okay? So now I'm asking the following question. When is it, okay? When is it that, oh, I see, there is a missing slide here. Okay, never mind, I'll tell you. When is it that the role player can guarantee, oh, okay? No, yeah, okay, so I'll use this here. So here are the payoffs, okay? They say they are in R2, okay? So this is one payoff, this is another payoff. Those are possible payoffs, okay? Those are the things written in the boxes of the matrix. Now, somebody comes and gives, so here's a question we are interested in. Somebody gives you a set, this set, call it C, okay? Nice convex set, let's say, okay? Closed convex set. I want to know whether the role player has a way to guarantee, and again, I'm using the word guarantee to say no matter what the opponents are doing, okay, that the average payoff is going to converge to the set. Okay, so this is the average payoff, is going to get closer to the set, perhaps go inside even or so on. That's the question I'm asking. Okay, so let's start with an easy case. The easy case is the following, that my set is this half space, where here is a random number 7, let's say. Okay, what does it mean? Okay, the guy does not, so he wants the average number of apples that he got not to be more than 7. He chokes on more than 7 apples. Okay, he does not want. So is there a way to guarantee that he's not going to get more than 7 apples on average? Okay, that's a question. Now, if we think about this for a moment, that's a question that has nothing to do with bananas, which is the second coordinate. So it's a question on apples. Apples are a scalar, okay, one-dimensional object. So in fact, it's very easy. The answer is he can guarantee in the long run that the payoff is going to converge to this half space, if and only if he can guarantee in the one-shot game that the payoff is going to be in the half space. Okay? No matter what the second player does, if he can guarantee that the payoff is going to be here, then clearly the average is also going to be here. If on the other hand he cannot guarantee, then the min-max theorem comes to our rescue. If he cannot guarantee it, the other guy can keep him away from it. That's again a use of the min-max theorem. So using the min-max theorem and law of large numbers again, you get this neat result, which is in fact quite trivial, okay? Which says that the half space is approachable, so the player can guarantee in the long run that the average is converging to this set, if and only if he can guarantee it in the one shot, which is called enforceable. Okay? Now clearly the geometry of the problem has nothing to do, it doesn't depend if the half space looks like this or if the half space now looks like this. Okay? If it's this half space. Okay? So any half space is the same. Okay, good. Now let's take C a convex set. Okay? So I want to know when is it that the rho player can guarantee that the long-run average payoff is going to converge to this nice convex set. So what's the answer? You probably guessed it. Okay? If and only if every half space that contains it, so I take this half space, and that should be approachable. And this half space, that should be approachable. And this half space, that should be approachable. So if all the half spaces are approachable, which by the previous slide means that they are enforceable in the one-shot game, then their intersection, which is a set C, is approachable. Now that's clear, right? Everybody sees the proof, right? What's the proof? Everybody sees it. What's the proof? Huh? And, okay, yes. So, continue. I mean, this I know. Next. What do you need? What's the next step? And if this is approachable, and this is approachable, then intersection is approachable. Except that's false. That's false. Sorry. Okay. Except that's false. The fact that a half space is approachable and another half space is approachable does not mean the intersection is approachable. Because, for instance, look at this game. Okay? Here it says 1, 0. Here it says 0, 1. Okay? So, is there a way for player 1 to guarantee 1 apple? Sure. By playing here, so the second player has no moves. There's no choices. So there is a way to guarantee at least 1 apple. How? By playing top. There is a way to guarantee at least 1 banana. How? By playing bottom. Is there a way to guarantee the intersection, which means at least 1 apple and at least 1 banana? No way. Okay? So the intersection of approachable sets is not approachable. So this theorem looks like one of those standard convexity theorems. It's not. Okay? But it's a nice way to put it. And in fact, the proof of Blackwell, or the argument, okay, why don't, okay, here I'm just, nice, you can see. Okay. Oh, here is the example. Yes, I knew I had it someplace. Okay. So the claim is this: if all the half spaces containing C are approachable, so if this one is approachable, and this one, and this one, and this one, if all of them are approachable, then their intersection is approachable. Okay? It's not enough that two sets are approachable, the intersection is. And the proof of Blackwell is very nice proof, because essentially what it works on the following thing. What is, oh, okay.
Here's some more.
Oh, okay. Okay, so here is the set. And essentially the way this works is like this. You look where the average payoff is now. We are at time t. If the average payoff is here, the guy is so happy that he gets drunk and plays randomly, arbitrarily. Doesn't matter. Okay? But if the average payoff is here, outside, then he says, I want to get to the set. What should I do? Well, what's the closest point in the set? This one. Then he draws the closest point. He draws a supporting. Sorry, can you see? I think you can't see it. Let's see if this color is better. Well, marginally better. Okay? Then he draws this half space, which is exactly perpendicular to this line segment joining them. And this is approachable. He's going to play exactly that strategy that is good for this half space. As a consequence, I'll already give you the proof. Where is the next payoff going to be? Someplace here. Let's say here.
Let's put it much farther away than the rest.
Okay. You can't put it in the basement. Why? Because the game is finite. The game being finite means there are only finitely many boxes. That means there are only finitely many possible payoffs. So everything happens in some big box. Let's assume the big box is the blackboard. Okay? Okay, put it here. No, here. Very good. Now, but I choose t. I'm going to tell you that the time at which this happened is 1 million. Since the time at which this happened is 1 million, what is the new average going to be? It's going to be here. The ratio of 1 to 1 million between those things. Okay, this point is clearly closer. Now, of course, one needs some computation and so on, but that's the idea. The idea is because this can, so of course, if this would be in the basement, that would not work. But because everything happens in a bounded set, then I get closer. But what happens is at every point in time, I change my strategy. I move with the set. I move with the averages. Okay? It's a very nice argument. Okay? Which I'm not going to give. Okay? But it's neat, and there are nice things coming out of here. Now, what does Blackwell have to do with forecasting? Okay? So let me, again, as I said, I can't, I have very limited amount of time, so I just, I'll pick your interest only. I'll just give you some things. Those who want to know details can come later. Using the Blackwell theorem, there is a way to look at all possible forecasts, 70%, 0%, 10%, 20%, and so on. And looking also at all alternative forecasts. So for example, in those days I made the forecast 70%. When I look and I see that in fact the average was 52% of rain, I would say, I should have said 50%. If in all those days instead of 70% I would have said 50%, I would be calibrated. And so you look for each forecast and each possible alternative forecast you could have done instead. And you define something which is called regret. And the regret measures how much you regret saying 70% those days rather than 50%. And then, using Blackwell, you take the vector of payoffs being those regrets. So it's a regret. When I said 70, why didn't I say 50? When I said 70, why didn't I say 60? When I said 50, why did I say 10? And so on. You look at all these regrets, okay? So you have 110 regrets, 11 times 10. Each possible forecast and each possible alternative forecast. You have 110 coordinates. And what you succeed in doing using Blackwell theorem, and the nice, not just using Blackwell, there is a whole construction and so on, is making sure that you have no regret. You never regret when you said 70% not having said 50%. That means that 70% was the best you could have done then. And in fact, that's one step. That step requires, at every step in time, solving an eigenvalue problem, a linear eigenvalue, computing an eigenvalue of a matrix 11 by 11, which is not bad. But forecasters are not as good as that. Okay? So there is a better rule, which you can use your hands. Okay? In fact, if you dig a little better into the problem, then it turns out that your forecast is always going to be based on two close by, like 60% and 70%. You're going to randomize among two neighboring forecasts. And the rule is there is some measure of the 50%, an excess or a deficit. There is an excess of deficit for the 60%, and you just play proportional to those things. There is a neat formula that one can write down, and really you need no calculator even. You can really do it with your hands. So that's really the very easy way to guarantee what was written here. Namely, no matter, so again, this is now, I'm giving you a constructive. I'm not giving you. I'm telling you that there is. So it's an existence proof of a construct. No, okay. No, that one can really write it down. So it's a very nice construction that gives us a nice rule on what to do every time. So I can open a forecasting. I can start going on TV. I don't need this. I don't need.
What is the rule? Can you tell us, without proof, just tell us what the rule is.
I essentially told you. You at 50%, you see that you are either in excess or in deficit, which means is it above the actual
For each number from 0 to for each multiple of 10.
For each multiple of 10, there is either excess or deficit. And you have to find two neighbors, I think, where there is a switch from excess to deficit. And there is always going to be one. And you now are going to play in the probability which are inversely to how big the excess and the deficit is. And that's a rule. Okay?
Have several alternations.
Doesn't matter, either of those. Okay? Okay? So just to... that's a nice, so by the way, doing all this using Blackwell, that's work of Andreu Mascolel. Much of what I'm going to talk here is joint work with Andreu Mascolel. So except for the last topic, everything else is with Andreu Mascolel. So all this connection to Blackwell and the actual way to do it with Blackwell, the actual constructive way is Andreu and me. The neat thing that I just told you where you only need two neighboring things is Dean Foster. Okay? All this calibration thing, there is it started with nice work of Vora, and Vora was here, right? He visited, Rick Vora.
Ricky
Vora.
Gave a little bit of a talk. He gave a talk in which he mentioned forecasting
Okay. So that's
You
info.
mentioned about 10 different papers that discovered Blackwell's theorem, rediscovered.
Rediscover, yes. Okay.
You were not one of them.
No, it probably was. I mean,
So anyway, the forecast, the neat rule that I just told you, where you only have to use 2 forecasts, that's Dean Foster. Okay, it's a nice paper. There's also one reference I can give. It's a 2-page paper doing that. Okay, now all this in fact came out from something else, which is, I mean, it's a side product of something else, which is the question of are there nice dynamics? We're not going to standard game theory, okay? Are there nice dynamics, or are there dynamics that people can play, or players in a game can play, that guarantee that they are going to get to equilibrium, okay? Now what's equilibrium? So the standard equilibrium that everybody knows is Nash equilibrium. So for those who don't know, so everybody knows except those who don't. So for those who don't know, I'll remind you what's a Nash equilibrium. So Nash equilibrium, if you have an n-person game, so it's an n-tuple of strategies such that no player can gain by changing what he does. Okay? The assumption is that if he can gain, then he's not going to stay there. Yes? He's going to move to some other place. What's going to happen, we don't know. So Nash equilibrium is a minimum requirement somehow. At least, there should not be any immediate gain. That one by changing, because each one is independent and can change what he does. If he has a way to change his strategy and get a higher payoff, he's going to do it. So that's a Nash equilibrium. Okay? Then there is another notion which is called correlated equilibrium. Anybody here knows what a correlated equilibrium is? So you know what? I have until 5 or what? Or 4:30 or what's...
well, I mean,
At 4:45 people will start.
yeah.
Oh,
yeah,
at 4:45, I see.
Start getting in.
So the question is, should I... No, so you know what? So there is correlated equilibrium. I'm not going to talk. Huh? You want me to talk about correlated equilibrium?
Yeah, talk about...
Huh?
You could just redefine Nash
No, I know what to... No. But if I start talking, I have so many nice stories about it that it... I'm thinking... Okay. So you know what? Okay. 3 minutes on correlated equilibrium. It's a good concept, believe me. It's a nice concept. And, for computer scientists, even Papa Dimitriou now is working on correlated equilibria, so that's a good sign. And Silvio Micali, yes, is now working very heavily on correlated equilibria. So if it got to computer science, that's okay. Yeah. Okay. So what's a correlated equilibrium? So we talked about Nash equilibrium, but now assume that before we play the game, we observe some things. For example, we observe the weather. Yes. And, if the weather is nice and Yuval and me have to play the game, then we have to go into our cubicles and play the game. It's a nice day. I say, I'll be nice to Yuval, let's play this way. But if it's, standard Seattle weather that I heard about, but I haven't yet seen, this kind of rainy and gloomy day, I don't know if it's correct, but that's what I've been told. Yes, you go to Seattle, it's not nice. Okay, so I don't see it yet. So forget all these games. I'm going, no. So it's a prisoner's dilemma. I'm going to play very tough and so on. Let's finish this. I don't want to be nice to him. Weather is not nice to me. Why should I be nice to him? Whatever. So, in fact, the fact that we are getting signals before playing the game. Now, it's very important that those signals do not affect the game. If they affect the game, of course, then there is no question that I should take them into account. But weather is not something relevant to the game Yuval and I are playing. That's my assumption. So those signals are payoff irrelevant. They do not affect the game. They do not affect the payoffs in the game. Nevertheless, we can use them to decide what to do. So on a sunny day, we can decide, for example, if you know the famous game, the Battle of the Sexes, yes? On a sunny game, we are going to go to the opera, right? And on a rainy day to the football, because we like getting rain, in the stadium, right? We like getting wet or whatever, yes? We can coordinate things on that. Now, those things are in fact, I told you that I'm going to tell you stories. So here's a nice story. It's not just, biological. in the forest in England, there are butterflies. I forgot the name, but I have the precise name of that for those who, so it's not a story. And those butterflies are in a very dark forest, okay? Now, Madame Butterfly and Mr. Butterfly have to meet for, obvious reasons. Where would they meet?
The opera.
Where there is light. That's a different opera, yeah. So, in the thick foliage, there are rays of light that suddenly go through. Yes? There is a small patch of light, very tiny because, it's England, forest, and so dark forest. So, when there is a patch of light, Mr. Butterfly wants to occupy that because that's where Madame Butterfly will come, okay? Now, what happens if two Mr. Butterflies are coming, okay? They can start fighting. Now, butterflies do fight, despite what you think that butterflies are nice and so on. Now, fight doesn't mean, that they take a gun and shoot. But, even starting to fly around and so on, in a dark forest, you are wasting energy. And that's very important, because that energy you rather spend with Mrs. Butterfly, okay? And not in fighting another Mr. Butterfly, okay? Energy is dark and cold, and, so you have to preserve energy. Fight is costly, okay? So now what happens when two butterflies are coming, that. So they can fight, or one will stay and the other will leave, okay? So somebody started doing observations. His name was Davis. So those are called Davis butterflies, but that's not a scientific name. And he looked, what happens? And what he saw, a very simple rule. That if a butterfly was there and the new one came, then the new one went away and the one that was there stayed. So you could say, oh, of course, sure. The one that was there was the big guy, and all the others, so the big guy stayed, and all the small ones that came saw the big guy, they ran away. So what did Mr. Davis do? He took the incumbents, those that were there, and exchanged them with those that didn't have patches of light. And he saw the same thing, that those who were first, they stayed, whether they were small or large. And the newcomers would go away. So that's a very nice coordination device. Okay? If somebody, you don't want to fight because that wastes energy. Okay? So the one that is there stays and the other one goes and tries to find something else. Okay? Another nice example that I had for correlated equilibrium, I spent some time at Harvard. Now, it's a boring place, believe me. But there was, at the time I was there was a very great team, Boston Celtics, NBA. I mean, it's not like today. I think they're probably the last spot in the league or something. Yes, at that time, Larry Bird. Anybody knows what I'm talking about? Yeah. Okay. No, I don't know. There are young faces here. So, Larry. Sorry. I shouldn't. Very young. Yes. I belong to the young, so it's okay. We are same equivalence class. So Larry Bird and Parrish and McHale, and going to the Boston Garden to see them play was really quite something. Now, the quite something was really the coordination among them. So in fact, let's make a stylized kind of story, So the Celtics, Larry Bird got the ball, and they start an attack. Now many teams you see here starts looking around. Oh, where is this? Who should I? No. He would get the ball, he would throw it. McHale would be in the right place to put it in the basket. Well, not always. It's still a game, yes, but with very high probability. Now, in fact, where would they go? Would they attack on the left or on the right? I'd say it's a very stylized kind of story. Now, I'm sure the other teams watched the replays, and it was probably 50% going to the left or the right. Okay? But somehow the Celtics knew, are we going to attack on the left or on the right? How did they know? I don't know. The first step of McHale or the finger of Parrish, I don't know, something. Somehow they had some coordination device. They knew how they are going to attack and what they are going to do. Because they played so many games together, by now they developed some signals. I'm sure you'd ask them, they wouldn't know what those signals were. But they had a beautiful coordination inside the team. Whereas from the opposite point of view of the opposite team, it was half-half. So that's exactly correlated equilibrium. So from the opposing team, left or right is half-half. All the Celtics, with probability 1 would go left, or with probability 1 would go right. And according to some signal that they got. Okay? So that's a nice coordinating device. So all this, what I'm trying to tell you, that correlated equilibria are all around us. In some sense, the Nash equilibrium is a very special kind of correlated equilibrium where either there are no signals or the signals are stochastically independent. Okay? There is no dependence between the signal that Yuval got and I got. Now that's a very, very restrictive situation, which in fact is very hard to find. if you try to think of a scenario where this is really the case, we all see the weather, we all read the newspapers this morning. I mean, those things, even when they do not affect directly the game, they will find their way into the equilibrium concept. That's very natural. So correlated equilibrium is a much more natural concept, we claim, than just Nash. Okay? So, why did I talk about correlated equilibria? Because all this black hole approachability and all this story that is here gives us some very nice dynamics, that converge to correlated equilibria in any game. And those nice dynamics are nice and simple in the sense that they are based on very simple measures of regret. I already talked about regret. Why did I say 50%? Why did I say 70%? I should have said 50%. So there are similar measures of regret when you played some action. Oh, I should have played a different action. You just measure those things, how much better you would have been had you done something different, and that is going to be the probability with which you switch to that other thing. Some very, very simple heuristics work and give you in any game something like this, which is a correlated equilibrium. Okay? Now, so that's something I'm not talking about, okay? Because if you remember the title of the talk, okay, not this one, but this one. Okay. You know what? Okay, so let me do something else. I know how I should do it. Just a moment. Part 5. Okay. Here. So now the question is this. It turns out, now that's an empirical observation on research in game theory, that it's very hard to find dynamics that lead people to Nash equilibria. Sounds like Nash equilibrium is a simple concept, but dynamically it's very hard to converge there. For simple games it works, but for more complex games it doesn't. On the other hand, there is a recent literature which provides nice dynamics converging to correlated equilibria. And the question is why? Okay? Now, in our paper that we in fact had not a footnote, a sentence that we put there, well, it's quite clear, we said, that it's hard to get to Nash equilibria rather than to correlated equilibria. And the reason we had in our mind was a purely mathematical reason. A Nash equilibrium is a fixed point of an n-dimensional mapping, which is in principle a very general mapping, has no special properties. Okay? Correlated equilibria, the set of correlated equilibria is a nice convex polytope, a solution of finitely many linear inequalities. So which one is an easier set to converge to? It's quite clear, yes? Nice things that are given by linear inequalities is much easier than going to fixed point. But that's not, I mean, that's a beginning of thinking about it, because we are not computer scientists that want to compute. So if our purpose was, let's compute a correlated equilibrium, or let's compute a Nash equilibrium.
Do you mean that it's easier to come up, for us to come up with some dynamics that would make us converge, that would make it converge to that? Or do you mean that it really is easier to converge? There's a question of how strong the attraction
I understand. So yeah, so I'm coming to that. So just 1 second, I'm exactly coming to this point. Okay. So again, if we are thinking computationally, we want to compute such a, so somebody gives us the game, and we want to compute a Nash equilibrium. That means computing a fixed point. That's much harder than solving a bunch of linear inequalities. Yes, that's we know for 60 years to solve that, right? When was linear programming, yes. We have nice algorithms to do that. It's very easy to do. Fixed points is hard, yes? Okay. That's not the point. That's something that says, well, this is a difficult object, this is an easy object. But that's not the point. The point is that this is the game. And it's not computing, but it's playing. Playing means every player is playing the game. And we want a dynamic where players are playing the game. Not that somebody comes and tells, you value do that, you do that, you do that, you do that, you do that. It's not, there is no dictator here. Okay? There is no supervisor that tells everybody what to do. Each player plays. Okay? Now, when each player plays, we want to see how those things are moving. Now, that's what I said. Is there a way to get dynamics converging to Nash equilibria? Okay? So the answer is, in special classes of games, the answer is yes. What are those special classes of games? I put here a few. 2-person zero-sum games, 2-person potential games, supermodular games, and lots of dots there. In fact, those lots of dots cover about 2 or 3 more cases, and that's it. I know one, in fact, I think, or 2, but that's it. That's the end of the story. Okay? So there are no nice dynamics working in general games. There are nice dynamics converging to Nash in simple games. In general games, no. Question why? Okay? So let's think about, here I hope I'm coming to what you had in mind. Okay? So now let's think what is a natural condition on dynamics that players play. Okay? So a very natural condition, I think, for people in computer science, if I'll say distributed, that will raise something that they know. Huh? Raise some antenna, yes. The basic assumption is that every player knows only his own utility function. Of course, if everybody knows everybody's utility payoff function, everybody knows, if everybody would know the whole game, then everybody could sit down and compute. And you need some way to make sure that everybody computes the same thing using the same algorithm. You know, it'll take them a long time, but they will get there. The problem is that that's not what they do. So when I play the game, I know what my payoff function is. Even that I'm not sure that I exactly know, because you have to take not just the material payoff, but my utility from that, and there are complications there. But let's assume I know that. For sure, I don't know what Yuval's or Jennifer, what somebody else's payoff is going to be.
Two-person game?
N-person game. Okay, I put 2-person here just for illustration, but there's nothing to do with 2-person. If it's zero sum and I know my payoff, then I know yours because it's minus mine. So that's a special case which explains why something that will come later is not contradicted by what happens for zero sum games. So if you may want to keep this in mind, okay, or not. Doesn't matter. It's not. It's not. But okay. So let's think for a moment. What's a general dynamic? Okay. So general dynamic in game. Okay. So delta of A1 is the simplex. So I'm thinking now of continuous time dynamics because it's easier to explain, and that was in fact the first approach to this issue. So that's what I'm going to write down. And 2-person is just for illustration. It's nothing to do with 2-person. Okay. So x of t is something that lives in the simplex of probability mixtures over the pure strategies of player 1, and y of t is the same. Oops. What happened to that A? Wow. It was there. I am sure it was there. I mean, this exists for 5 years, this portion of that, and I'm sure. So probably I corrected something at some point, and I erased that. Okay. So that's not a footnote. Yes, this is an A2. Okay. Okay. Yeah. Yeah. Well, I know in China you come with something like this, and all the symbols suddenly become cats and things like that. It's very fun. You have to be careful. But here it's Microsoft, so I think it's my computer, so it's probably okay. So x of t is what player 1 does at time t. Y of t is what player 2 does at time t. As a function of that, so that's a state. As a function of that, I'm looking how player 1 is going to change what he does. That's x dot t. Yes, derivative of x with respect to t. I'm looking at the dynamical system. And the same for player 2. His change in y is a function of where they are now. And, of course, it's a function of the game, which is represented by the 2 payoff functions. So u1 and u2 here are the payoff functions of the 2 players. That's a general dynamic. Now I want to talk about the condition I talked about, and that's an uncoupled dynamic. What's an uncoupled dynamic? This is an uncoupled dynamic where player 1 can only use his own payoff function u1. Player 2 can only use his own utility function u2. Player 1 cannot use u2. Player 2 cannot use u1 because they just don't know it. Okay, that's decentralization.
This excludes zero sum because.
Sure, of course.
Exactly. It doesn't exclude. It doesn't exclude. Sorry, it doesn't exclude. If the game happens to be zero sum, then knowing u1 means that you also know u2. So it's fine. I mean, it doesn't exclude. It just said it becomes a triviality. It means that there is no restriction there. Okay? But so let's understand what this restriction is. That means that if there are 2 games where my payoff function is the same, but Yuval payoff may be different in the 2 games, but my payoff is exactly the same payoff function, and we play exactly the same, then what I'm going to do next time is the same, regardless of the fact that it's a different game, and Yuval may play differently, but I have to do the same. Now, at that point, of course, we are going to get a new state, and things may change. So, of course, it's yes, but now, if you want, y may represent, for example, an average of the history, and you can move in A1 and A2 maybe. You may learn something. These are very abstract spaces, so you can embody here lots of things. Okay, but.
Sorry, does U1 mean the whole function?
Yes, U1 means the function. It's a function from A1. That was in one of the very early slides of this presentation, which I'm sorry. So just to make sure that. Okay? No, here.
Can you see what UVal has actually got paid?
UI, no.
So you can't do that.
So UI is a function from A1 cross A2, or if you want the simplex. So the only thing I see is what UVal does. The only thing UVal sees is what I'm doing. Why I'm doing what I'm doing, what kind of payoff I'm getting, how rich am I getting, or how poor am I getting, that it doesn't observe. Okay? He only observes what happens.
See what car you're buying.
Yes, but you don't know how much debt I'm going into to do that, and you don't know how much I'm paying for it, and you don't know what kind of deal I got, and you don't know why I'm buying this car. Maybe it's just it's not that I like the car. I want you to envy me. Yes, that's my utility. I don't get utility for driving this nice car. I just want you to think that yes, okay. But you don't know. Sorry.
You have lost all your memory.
I've lost. What was the question? Sorry.
Okay. Memory, right? We don't remember how you were played yesterday.
Yes, but as I said, you can embody, as I said, since A1 and A2 in fact can be very general, you can embody into that much more things. But let's assume that that's indeed the case. Okay, now, if you think about essentially all the dynamics, best reply, better reply, payoff improving, monotonic, fictitious plays, you get all replicated, all the dynamics, almost all are indeed uncoupled. They are all uncoupled. You check them. What happens is that the player sees the situation and reacts to it as a function of his payoff function, usually in a way that improves his payoff, yes, but not taking into account what the other guy does. So, and it's important to understand, uncoupledness says nothing about rationality, maximizing or things like this. It just says it's informational restriction. Okay. Now, we want to converge to Nash. Okay. Now, there are games where there are many Nash equilibria. And I may converge to one, and Jennifer to another, and we'll never meet. Yes, she will go to the opera, I'll go to the football game, and we're not going to be in equilibrium. That's tough. Okay? So, since I want to see what this condition is, let's look at games that have only one Nash equilibrium. If there is only one Nash equilibrium, and I can find a dynamic converging to equilibrium, I know where it should go. There is no dispute. Okay? So there is no coordination problem. Okay? And I'm going to say that the dynamic is Nash convergent if it always converges to the unique Nash equilibrium in such a family of games. Okay? And there is also some regularity condition that, I'm assuming that it's a hyperbolic and so on. Don't want to get into trouble because anyway, it's just conceptual here to see what happens. Okay. Here is the result. There exists no uncoupled dynamic that guarantee Nash convergence. So if you look in the class of dynamics that are uncoupled, where what I do depends only on my payoff function, what Yuval does depends on his payoff function, what Jennifer does depends on her payoff function, then you cannot find any dynamic satisfying this that is guaranteed to converge to Nash equilibria, even when you look at this subclass of games where there is a unique Nash equilibrium. In fact, you just look at the neighborhood of just one game. So let me be even more precise. There are simple families of games. In fact, it's one game and a small neighborhood. That's it. So I show you that already there you have trouble. So clearly you have trouble over much bigger families. So there are simple families of games where each game has a unique equilibrium, and that unique equilibrium is unstable for every uncoupled dynamic. So what's going to happen is you may come there to the equilibrium, but it's unstable. You're going to go out. Maybe you'll come back again, but you'll never stay there. You're never going to converge to that. So uncoupledness implies that you cannot converge to Nash equilibria. Okay? Now, that says something. Because remember, I said that all those nice dynamics in the literature, they are uncoupled. So don't try to make them go to Nash equilibria. You won't succeed. You'll be surprised how many PhD theses were written saying, here is a nice dynamic. Look at, I don't know how to prove that it converges to Nash. But in all the games I tried, it converges to Nash. And look at my simulation in this game. And look at my simulation in this game, converges beautifully. But I assume that a little more work I will be able to prove. No way. Those dynamics are uncoupled. It won't work. Now we know. Yes, but... Sorry?
There may be particular games.
Sure. Zero-sum games, it works. Potential games, it works. There are classes of games that it works, but they also are very limited classes of games. Those were at the beginning. Okay? So again, it's not, as I said, in fact, the example is not a very, there is an example of a game in the neighborhood, but there is nothing pathological about that. You have things like this everywhere. Okay, so those are examples, say, with a unique mixed equilibrium or other things like this. So it's not like there is one counterexample in the world and that's it. Okay, this is a common phenomenon. But
Wait,
okay.
I'm confused. So
Okay.
go back to the statement.
Yes.
The previous one. Okay. So we've just been giving the examples that do converge, that are uncoupled and do converge.
For very special, no, they don't converge to Nash. No, that's the point.
They converge to something else. Then.
Nobody says they converge. They may cycle around all the time. Sorry. There are classes of games like two-person zero-sum games where there are nice dynamics, fictitious play. Doesn't matter what it is. Nice dynamic that is guaranteed to converge to Nash equilibrium.
So what you're
but
saying
it's
by
only
simple families is that
not every simple family. I give you a simple family. I build you a simple family. In fact, as I said, it doesn't say it here, but this is not one pathological example. I can build you, lots of simple families like this, which is always one game. Properties, for example, one game with a unique mixed Nash equilibrium and an arbitrarily small neighborhood around it. That's enough to show that uncoupled dynamics cannot converge to that unique Nash equilibrium here. Cannot. No matter what dynamic you are going to invent, if it is uncoupled, then this unique Nash equilibrium is going to be unstable for that dynamic. Okay?
And for that,
Now,
the
there are,
payoff function.
doesn't matter what they are. Yes, arbitrary.
No, but it does depend on the strategies, right? So you're saying there is, because maybe, I mean, it does depend on the payoff.
Sure, I mean, depends. I'm giving you a game, okay? I'm giving you a game, and I'm saying in the neighborhood of games. Or if you want a set of games containing something, okay? And that game, if the dynamic is uncoupled, means, remember what uncoupledness says, that if in that game you behave this way, in a nearby game where I change your payoff but not mine, I have to behave exactly the same, okay? That restriction makes the Nash equilibrium unstable, the unique Nash equilibrium unstable, dynamically unstable. Okay? Namely, you cannot have, if you want, you cannot have eigenvalues being negative real part. Okay? There is always going to be one positive. There is always going to be a direction you are going to run away. Okay? That's technical thing. Okay? Okay. Now, Now I'm going to switch. Yes, I still have 2 hours to talk, right? Okay. So now.
So is it possible to tell us what's one of the
No.
bad games?
Not now. Not now. Not now. Not now.
But
But.
you first argued that Nash equilibria were stupid equilibria to look at, and then you argue, and then you argue that
No.
that
Listen, the whole world.
dynamics were not going to
The
be
whole world looks at Nash equilibria.
I
So I'm
know
not
they
saying that
do.
they are
I know
stupid.
they do.
What I'm saying is that they are very restrictive, and what I'm also saying is that they are dynamically hard to reach.
Right. Okay.
Okay? Those are separate issues. Those are separate issues. Those are separate issues.
Yeah.
Okay? Now, okay. So now,
are you going to tell us about uncorrelated?
no, okay. So now I can do 2 things. Okay. Now I can explain to you with a nice, okay, so here is a choice because I can't do both. One is I can explain to you, so those dynamics were continuous time, which doesn't matter, that was convenient, you can do it in discrete time, but they were deterministic. And the question is what happens if you can have stochastic dynamics? And then one can see really how uncoupledness plays a role. That's one thing I can talk about. The other, I can talk about communication complexity of reaching equilibria, Nash and correlated, in uncoupled situations.
I vote for the first one.
Wait. What about the rain?
No, I really want to go back to work done.
There is sort of.
We're going to
I didn't
schedule
like
more
the
of
rain.
it.
Okay.
But why don't you just do the
Okay.
first one?
I
Okay.
don't like the rain.
Okay.
So when
You don't like the what?
I don't like this measure for the rain, and he said.
Okay, I said, okay. You know what? During the question period, you ask and I will reply. I guarantee I will reply to that, okay? But so it's on your time, not on mine. Okay, so here is a repetition of what was said. So the dynamic process is uncoupled if the moves of each player do not depend on the payoff functions of the other players. Okay? So that was what I told you about. As I said, it's an informational assumption. Most dynamics are uncoupled. Okay, this repeats. So here is the result from the previous paper. In deterministic continuous time setup, there are games with unique Nash equilibria for which no uncoupled dynamic can lead to Nash equilibrium. Okay? Okay. And here we are going to talk about discrete time and stochastic. So here is a model. So we are talking about an n-person game in strategic form. So the players are 1 to n. And let's say that the action of player I is AI. Just a few symbols. Don't worry. Nothing heavy. Okay? And the payoffs, UI, is a function of the actions of everybody. That's what makes it a game rather than a simple optimization problem. What I get depends on what everybody else does. Okay? And we are talking about discrete time dynamics. So AIT is what player I does at time t. That's the action that he does. Of course, you can choose it probabilistically. So that's a realized action, what he actually played. Okay. Okay. Now, to define this uncoupledness formally, let's fix a set of players and let's fix their action, their strategy spaces. I'm saying, okay, I'm going to use now the word action to distinguish between what they do in the one shot. In the one shot, it's action. In the repeated situation, the dynamic situation, I'm going to call this strategy. But okay. So what's a general dynamic? A general dynamic tells player I what to do as a function of the history, what has happened up till that point, and the game. Of course, same history, but different game. You will react differently, right? Okay? So what's the game? The game are just the payoff functions of every player, because remember, the players and the action sets are fixed, so the only thing that changes from game to game are the payoff functions. That's the way to formalize what I want. What's an uncoupled dynamic? Very easy. You can only put here you can only put here UI. Okay? That's it. Not the payoff functions of the other players. So let's start with the simple thing and the only one that I'm going to do. Okay? Let's look at games that have a pure Nash equilibrium, just to fix ideas. Okay? So let's consider games possessing pure Nash equilibria. What would be the simplest possible, the simplest possible dynamics are ones where you don't even look at what happens. Okay? Now, you don't expect those to converge to anything. If you play constantly, regardless of what happens, then clearly there is no hope to converge to Nash equilibrium. So the simplest reasonable dynamic was where you take into account what happened only in the last period. Okay? So that's your memory. Now it came back to me. Yeah. Okay? So the simplest uncoupled dynamic is a dynamic where what player I does at time t is a randomization that is a function of the n tuple of actions played at time t minus 1 and his own payoff function. Okay? So that's a one recall strategy. Okay? You only look at the last period. And notice also that I make it simple stationary. It should not depend on calendar time. Okay? Now, it should be quite clear that if somehow they go to a best reply and so on, that thing, if there is a pure Nash equilibrium, should converge to it, right? That's, you sort of see it, right? Okay. There exist no uncoupled, one recalled dynamics of this sort that guarantee almost sure convergence to pure Nash equilibria in all games where such equilibria exist. So the answer is no. That's not true. Okay? And let me explain to you why, because that will give you a hint on what uncoupledness buys. Okay? I think it's a nice... here is a simple game. It's a two-person... you probably need to understand the statement of the theorem. I'll come back to it, but let me explain it with the example. It would be easier. Okay? You live in 3 minutes or something, so... okay. So here is a two-person game. Okay? As you can see, it's a matching pennies, and there is an extra row and column, and there is a unique Nash equilibrium here. It's a unique pure Nash equilibrium here. It's this 1, 1 here. Player 1, if he deviates, is only going to get 1. Player 2, if he deviates, is only going to get 1. So nobody wants to deviate. Nobody has reason to deviate. That's a unique Nash equilibrium. Everything else, one player can gain by deviating. Okay? Now, let's assume by way of contradiction that there is a dynamic which is uncoupled. So every player can only use his own payoff function, such that it only depends on what happened the last period, such that with probability 1, you converge to this, no matter where you start. Okay? So here is the game again. I didn't cheat. It's the same game. But since I didn't do anything with that one, this is the game. Yes? Well, I can only say maybe I put a different game. There is no Uri Geller here. Yes? No magic. Okay? So here is the game. Now assume that that's where we are at period t minus 1. They played R1, C1. Okay? Notice that player 1, the row player, is best replying here. Namely, against C1, playing R1 is the best. R2 and R3, the other two actions are worse. He only gets 0. Correct? So he's best replying. Then I claim he's not going to move. He's going to stay and play R1 next time also. Well, do you say yes? Why? You say yes, yes. You are Okay, that's okay. Let's see why, okay? Here is where uncoupledness is going to come in, okay? Because let's change the payoff function in the following way. Look what I do. Can you see? I've changed the 1 and the 0 in this cell and this cell, okay? So what I did, I just changed the payoff of player 2 in 2 cells. I could have done more, but I did just this minor change. The payoff of player 1 is the same matrix, so it didn't change. Okay? Now, in this new game, this is the unique Nash equilibrium. Now, from the point of view of player 1, it could well be that this is indeed the game. If this is indeed the game, and that's a unique Nash equilibrium, if he now would next time move away with positive probability, since we are talking about stationary strategies, it's going to do this every time. So every time they are here, they are going to move away with positive probability. They don't converge to this point. So he cannot move. So consequence of, okay, that's what it says here. So the consequence of uncoupledness is, if in this game he's not going to move, he could not move in the original game. Okay? So that means that if player at t-1, the row player is best replying, he has to do the same thing next period. Now that clearly is true for both players. So player who is best replying cannot move. That's what uncoupledness buys you. Okay? So now if I take the game and I show you in each cell which player can move or which player cannot. So here, player 1 cannot move, so you can only move horizontally. Here you can only move vertically. You see that unless you start here, there is no way to reach that point.
That's a cute way.
Okay? Now, you may be unhappy with this example. I mean, at least we were unhappy with this example, because that hinges very much on everything being here 1 and 0, and it's very important that this one equals this one and this one and so on. So it's a very non-generic situation. So here is a generic example with 3 players. Okay? So now here it's also you have numbers 0, 4, and 2, but here you can perturb any number you want. The thing will not change. Okay? So it's nothing to do with that thing. Okay. So let me remind you. So let me say now what we have proved.
There's no way to reach the Nash equilibrium, right?
So what I've shown is, if you are looking at dynamics that are uncoupled, okay, so let's see what we've shown. If you look at dynamics that are uncoupled, so you can only use your own payoff function, not Jennifer's payoff function. Okay? You only look at what happened last period, and it's stationary. There is no way you can guarantee convergence to the unique Nash equilibrium, to pure Nash, sorry, not unique, to pure Nash equilibria in games with pure, of course, if there are no pure Nash equilibria, I don't say anything.
So you want to say in some games where such equilibria exist, not in all games?
You cannot guarantee in all games, which means in some games it's not. Guarantee in all, then you cannot guarantee in all. Means there are games where it only, of course there are games where there is a dominant strategy, and those whatever you do it's going to converge. Yeah. So no, I think grammatically the statement is correct. You are misled by it, but you understood it correctly. Yes, you understood it correctly. Yes.
I would put in some games there such.
That guarantee. There are no. That guarantee. The no applies to everything written here. What is it here? It's not true. There is nothing guarantees in all games.
The games are hidden in the UI.
So okay. Now, in some sense, that parallels. It doesn't parallel mathematically. It's a very different kind of argument, but it's parallel to the result I just showed you in continuous time. Okay. Now let's move to 2 recall, and I'm only going to go up to 10 because I only have 10 minutes, right? No, I'll stop at 2. So what's 2 recall? You look at the last 2 periods. Okay. You can do it. So if instead of 1 you look at the last 2 periods, you can do it. And let me tell you how. Very simple. In fact, we start with something very complicated and slowly, at the end it's extremely simple. Here is a strategy. So what's a state? The state is what both players did in the last 2 periods. That's what you know. Okay, and as a function of this you have to decide what to do. Okay? Now, so here is what I'm going to do. If everybody, yes, we have n players, yes? So it's not 2 players, it's n players, yes? So but everybody sees what happened in the last 2 periods. I have a window of 2 periods. If everybody played exactly the same in the last 2 periods, okay, so there was a repeat, then player I, am checking whether what I did is the best reply to what the others did. If my answer is yes, I do it again. Okay? So if in the last 2 periods a pure Nash equilibrium was played, everybody is going to say, aha, this was repeated twice, it's time for me to check. Am I best replying? Yes, I am best replying because of Nash equilibrium, so I'm going to play it again next time. So what's going to happen? Next time they play again the same. They see the same window, so the window moves one, and this keeps staying there forever. In all the other cases where this doesn't hold, just randomize. Uniformly or anything, as long as you randomize with positive probability on everything, you are eventually going to get to such a state, and that's it. You can't do it much simpler than that. Okay? Okay. Yes, but there is no way. Okay, so now let me jump to the end. Okay. I'm going. Yes. Yes. Here is a summary of the results, which you haven't seen, yes? But I will.
So
okay.
you mean your yes, or you just mean yes if
No, the point is this. The point is, okay, so the point is, in fact, okay, I'll tell you what's on the next slide. The point is that there is no way to, really what you are doing is exhaustive search. That's what you are doing. It's whether you do it randomly or whether you go one by one or something, you have to do exhaustive search, and you also have to have a way to, but it's not in, but why recall one is not good enough? Why can't you do it as recall one? Why do you need recall two? Because you need a way to coordinate the fact there is a search and there is a checking. Are we at equilibrium? And you need to have some way to coordinate the checking. Because if I'm staying there because I think it's good and you are moving, then we are going to go around and never reach an equilibrium. So recall 2 is enough for that when we are talking about pure. Okay? But now when we are talking about, so here is the other results that I haven't shown you. So if the recall is 1 and we are talking about pure equilibria, you cannot do it. But if recall is 2, you can. If you are talking about mixed equilibria, turns out you, instead of recall 2, you are going to have recall 20. Depends on the kind of precision you want and so on. You can, or 30. I mean, you can do a similar construction. There exists a finite recall dynamic that of the same kind that will guarantee convergence to mixed Nash equilibria. Okay. The problem with that, however, the problem is So that, however, here is another result that I don't talk about. If you are convergence to Nash equilibrium, say we're playing matching pennies, which means I have to do half-half, Yuval has to do half-half. Now, I would say that I really converge to this half-half provided that I am playing half-half independently of Yuval. Okay? So it's not enough that my frequency of playing is half-half and his frequency is half-half. I also want the independence. Turns out you cannot reach this with finite recall, no matter how large that recall is. You need finite memory. What's the difference? Finite recall is this moving window. With moving window of arbitrary size. So you take finite size, moving window, there is no way to guarantee that I'm going to play my half-half, Yuval is going to play his half-half, and those things are going to be in the limit independent. Okay? But if instead of moving window, I have finite memory, I have an automaton, then one can do it. Okay? Again, I'm not saying anything about that. And, in some sense, let me just jump to the final, here is the important, speed of convergence, yes. Everything here is exponential, by the way. When you talk about correlated equilibria and so on, everything there is polynomial. Speed of convergence there is polynomial. Okay, things are behaving nicely for correlated equilibria and unnicely, which means exponentially unnicely for Nash equilibria. And the reason is that you really need exhaustive experimentation. There is no way that you can reach in an uncoupled situation Nash equilibrium. Okay, so that takes exponential time. There is no escape. And in some sense, this is, this belongs to, we have dynamics out there, lots of them. Everybody can invent his own dynamic, yes? And the question is, can we, so we have this huge class of dynamics. Okay, those are dynamics, no hope that they can converge to Nash. If you want convergence to Nash, don't look there. Here, on the other hand, I know that there are such dynamics. I'm not saying that the dynamic I told you is recall 2 is a very natural dynamic or something. On the other hand, it's not far-fetched, yes? It has a nice flavor to it. But at least it says in that class, finite recall, you can obtain so much. But you cannot obtain independence. You need to go to finite memory and so on. So you really want to have classification. You want to know in what classes of dynamics you can obtain what kind of properties. And that's where this thing belongs, okay? And communication complexity is too complex for now, so I think I'll end here.